You see, I keep wondering about this tiny traveler from the deep dark between the stars, and perhaps you've wondered too. What does it really mean when an object like 3I Atlas drifts into our cosmic neighborhood, carrying with it a story written long before our world even formed? And why, on that quiet day of November the 11th, did it reveal something so strangely beautiful, an anti-tail leaning sunward, as if pointing back to the very star it was fleeing? You know, there's a kind of hush that falls over you when you look at something like that. A hush filled with questions. How does a body that small remain whole after swooping past the sun? Why does its dust stretch and fold into shapes that defy our expectations? And what secrets might still be locked inside its icy core? Secrets shaped in a distant system we may never see. I suppose that's the thing. Interstellar objects feel a bit like messages written in a language we're still learning to read. They arrive quietly, unannounced. And suddenly, the familiar rules of our own solar system begin to tremble just a little. And, as you picture 3I Atlas gliding away from the sun, still intact, still shedding streams of dust that play with the geometry of light, you might feel that same mixture of curiosity and reverence. Time, after all, is not just a ticking clock. It's a landscape these wanderers cross, carrying memories of frozen epochs, older than our species, older than our planet, older even than the shapes of our constellations. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So, let's continue. Well, you see, when we talk about that moment on November the 11th, the moment when new images of 3I Atlas quietly shimmered into view, we are really talking about a kind of cosmic whisper. A whisper that says something like, "Look again, look more closely, because the universe is not finished surprising you." And, as I think back on those observations captured by David Jewett and Jane Liu using the Nordic optical telescope, I can almost imagine the hush inside the control room, that subtle breath people take when data begins to reveal something unexpected. Something that, for a brief second, almost feels like it should not be possible. Because there it was, drifting through that cold sunlight, still one single intact body even though it had swept through Perihelion 2 weeks before. And you know, most of us had simply assumed it would not make it. Small interstellar objects, especially those carrying volatile compounds, usually fracture or crumble or disperse into clouds of dust when they swing that close to the sunday. It is what we have seen again and again in the comets of our own solar system. But 3I Atlas did not crumble. It held itself together, and perhaps that is the first sign that we are dealing with something that remembers a different birthplace. A different kind of stellar nursery where pressures and temperatures pushed materials into forms our system rarely produces. The strange beauty of that day was not only that 3I Atlas remained whole, but that it carried behind it a luminous sheet of dust that did something visually uncanny. Dust that stretched not away from the sun, but appeared to angle toward it. And, that sunward slant made it look, in the images, as if the tail were flowing in reverse. As if this interstellar visitor had turned its back to the void and leaned toward our star for one last lingering moment. Now, of course, the science behind this effect is down to geometry and perspective. The anti-tail lined itself at roughly 106 degrees, a direction that almost perfectly matched the sun, which sat near 115 degrees from the telescope's point of view. So, when the camera captured the scene, dust that was actually spreading out in the orbital plane appeared to flare inward, creating a shape that seems to contradict what we know. And that is the thing. These illusions born from the dance of light and dust are reminders that our eyes are not always faithful narrators of the cosmos. They offer beauty first, understanding second. But even once we understand, the beauty remains. Well, you see, for astronomers, the real shock of that moment was not the anti-tail itself, nor the angle of the dust, nor the peculiar symmetry hidden in the images. It was that subtle but undeniable truth that 3I Atlas was there as a single, compact structure. Because by the time a comet swings near its perihelion, the stress becomes enormous. Temperature gradients ripple across its surface. Jets erupt from patches of exposed ice. Material fractures, expands, sublimates, and erupts. If you imagine a fragile snowball carried too close to a bonfire, you are not far off. And yet this wanderer from the space beyond the sun's sphere of influence passed through all of that and emerged still holding together. As I think about Jewett and Liu staring at their observational data, I imagine them trading glances, wondering if the next update would reveal the first signs of disintegration, wondering if the nucleus would show cracks, if the coma would thicken into a cloud that signaled collapse, if the brightness profile would shift. But nothing of the sort announced itself. The structure remained sharp enough to suggest unity. The jets, though faint at that angle, seemed to accompany rather than unravel the core. It was as though 3I Atlas were whispering not yet, not this time. And perhaps what moved Avi Loeb when he later commented on these observations was that this behavior does not quite fit with what we expect from cometary physics as we understand it. We have models built on decades of data from solar system comets. We have watched countless objects break apart, sometimes spectacularly. We saw how comet Ison fragmented near the Sunday. We witnessed the collapse of smaller comets whose weak structural cohesion could not withstand the intense heat. Even in missions like Rosetta, when the spacecraft approached the nucleus of 67P, scientists saw cracks that widened simply due to sunlight heating the surface. And yet here was 3I Atlas, coming from a completely different star system many light-years away, carrying dust and ice forged in conditions we can only imagine, surviving a perihelion passage as if held together by something stronger or stranger or simply unfamiliar. You know, that makes you ask bigger questions. What kind of environment shapes such a body? What sorts of pressures or temperatures or chemical processes might allow an object only a few kilometers across to endure forces that destroy many local comets? And perhaps the more philosophical question lingers beneath those scientific ones. When something travels so far, for so long, does the long voyage itself shape it into something more resilient? Something that has already faced storms and collisions and stellar winds stronger than those it meets in our own system? Well, I suppose that is part of the story of interstellar objects. They are forged in environments we cannot easily reconstruct. Their histories are written in places our telescopes can barely glimpse. And when they finally pass near our sun, briefly illuminated, they let us read only a single sentence of an ancient cosmic narrative stretching across epochs. A narrative older than our planet, older than our oceans, older even than the continents themselves. As Jewett and Liu processed the images from the Nordic Optical Telescope, they found that the dust envelope was stretched wide across a span of hundreds of thousands of kilometers. A vast, soft halo etched into the night sky. You can imagine it as a kind of cosmic breath, frozen in motion, soaking up sunlight while telling the story of sublimation, rotation, and momentum. In that halo, the dust grains are pushed outward by the faint but steady pressure of sunlight. But in the plane of the orbit, where larger grains settle and move more sluggishly, a long sheet of material can form. And when seen from the perfect angle, that sheet becomes the anti-tail. This is what makes astronomy so deeply human. We are always trying to interpret shapes seen from impossible distances. We turn faint traces of light into maps of worlds we will never walk upon, and in moments like these, the line between perception and reality becomes thin. A tale that appears to defy physics really obeys every rule. It is our vision that needs to adjust, our understanding that needs to widen. As the data continued to arrive, scientists noted that the inner coma remained relatively compact. Not sharply bounded, of course, because comae rarely are, but intact in a way that suggests a nucleus that has not begun to shed large fragments, and that is unusual, especially 2 weeks after perihelion. During that period, thermal waves propagate downward into the nucleus. They destabilize structures. They release pockets of gas. They open fissures. Many comets become more active in the days after perihelion, not before it. Yet, 3I Atlas gave no sign of that kind of runaway disruption. You know, when we think about this, we are really thinking about how alien this object truly is. Not alien in the sense of intelligence or intention, but alien as in formed beneath a different sun, sculpted by a different gravity field, tempered by collisions in some primordial disk that has long since dispersed. Every comet carries the memory of its origin, but interstellar comets carry the memories of worlds we may never see. And somehow, the memory encoded in 3I Atlas seems to include resilience. There is something quietly moving about that. The way it traveled between the stars, crossing the cold gulf where the nearest photon may take years to arrive. The way it drifted along, untouched by the warmth of any sun, until it finally reached ours. And then, instead of breaking apart, it greeted the sun with a spray of dust that formed that magnificent structure caught on camera, a reminder that even in the void, things endure. And, those first images on November the 11th were only the beginning. Once astronomers confirmed that the anti-tail was real and not an imaging artifact, once they saw that the nucleus was still whole, once they measured the angles and brightness profiles, a deeper sense of curiosity settled in. Because if the first hint is that 3I Atlas survives far better than expected, what does that say about its composition? About the energy it stores? About the internal structure that holds it together, even under intense heating? Perhaps this is where the real story begins to open, the story that leads us into the deeper chapters. Because if Chapter 1 is about that moment of shock, that instant when we realize 3I Atlas defies our immediate expectations, then the next step is to understand what that defiance reveals about the physics of dust, gas, and geometry. The anti-tail itself invites us into that exploration, into the dance between light and matter that paints such strange shapes across the sky. Shapes that seem impossible until we understand the angle of our own gaze. And as we move forward, we will follow that dust, follow that geometry, and ask what the universe is trying to show us in the delicate structure trailing behind this interstellar wanderer. Well, you see, when we left off, we were standing right at that quiet boundary where astonishment gives way to deeper curiosity. The moment when you realize that the sight of 3I Atlas, intact and stretching a soft luminous sheet of dust toward the sun, is only the beginning. And perhaps what makes this next part so compelling is that the anti-tail itself, this seemingly impossible gesture of dust leaning sunward, is not a rebellion against physics at all. Instead, it is a testament to how the universe plays with light and perspective, reminding us that our position in the cosmos shapes everything we see. You know, if you imagine yourself seated beside me under a calm night sky, gazing up at the path of this interstellar traveler, the first question you might ask is something like, how can dust flow toward the sun when sunlight always pushes dust away? And that is the thing. The dust is not flowing inward at all. It only appears that way because of where we stand. The anti-tail is not an actual reversal of physical motion. It is an illusion born from geometry, an effect created by the way sunlight scatters off dust grains that are arranged in the orbital plane behind the nucleus. Larger particles, heavy and slow, tend to spread out along that plane like grains settling into the grooves of a pastor. Celestial record, and when Earth, Sun, and comet line up just right, these particles reflect sunlight back toward us in such a way that the tail seems to point into the glow of the sun itself. Well, once you see it that way, the mystery changes shape. It becomes less about violation and more about elegance. There is a quiet poetry in that dust sheet, stretched thin across hundreds of thousands of kilometers, catching sunlight the way morning mist might catch the first light in a mountain valley. It reminds you that the universe is always performing, always crafting illusions from ordinary mechanisms that become extraordinary only through the lens of distance. You see, the dust in the antitail is not freshly launched material racing backward, but older, slower, heavier grains that have lingered in the orbit like footsteps trailing behind a wanderer. What we see is the trail itself, lit from the perfect angle so that it looks as though the footsteps are leaning toward the rising sun rather than away from it. In our own solar system, this isn't entirely unprecedented. There have been comets with anti-tails before. Comet Arend-Roland in 1957 offered a famously dramatic example, when its anti-tail swept across the sky like a startling spear of light. Then again, in 2013, Comet Ison displayed a faint one as it plunged toward the Sunday. The mechanism was always the same: geometry, perspective, and the slow drift of larger dust grains lying in the orbital plane. But with 3I Atlas, the elegance is heightened by its interstellar origin. Everything about it feels like a message from somewhere far beyond our familiar sphere. And when such an object writes a shape into the sky, even an optical illusion becomes a kind of cosmic signature. Imagine for a moment those dust grains gliding through space. Some of them might be older than the sun itself. They may have formed near a young star that has since gone quiet, or in the outer reaches of a planetary disk that never gave rise to worlds. They drifted inside the nucleus of 3I Atlas for millions or perhaps hundreds of millions of years, locked within its cold interior until the sun's warmth finally released them. And then, carried gently along the orbital plane, they became part of that magnificent optical effect. There is something deeply moving about that. Dust older than the solar system falling into our view for the first time, forming shapes that trick the eye but reveal truths about how light behaves on cosmic scales. And that's the thing. The antitail reflects sunlight differently from the regular tail, which is pushed outward by radiation pressure. These larger grains, too heavy to be shoved immediately outward, fan out along the path the comet has already taken. So, when Earth crosses the comet's orbital plane, the dust appears to align in a straight, sharp feature, sometimes even sharper than the main tail itself. This is why antitails often look like rigid beams, whereas the regular tail looks soft and flowing. The regular tail responds to the pressure of light, like a curtain blowing in the wind. The antitail sits rooted in the geometry of the orbit, rigid and skeletal. And, when you consider the exact angles involved in the 3I Atlas observations, the effect becomes even more striking. The sun lay at about 115 degrees from the line of sight, while the antitail aligned at roughly 106 degrees. That near alignment, that delicate difference of only a few degrees, created a visual trick that almost made it seem as though the dust was leaning back into the brilliance of the Sunday. It is like looking down a long reflective corridor, where even small shifts in position change the entire image. If you close your eyes for a moment and picture this, you might see 3I Atlas gliding through the darkness, releasing dust that settles behind it like a path drawn across the void. And when the sunlight catches that path at just the right angle, it flowers into an arrow of brightness seeming to point the wrong way. It is not wrong, of course. It is simply telling a story we must learn to read. Perhaps what I find so enchanting is how this effect transforms something ordinary into something wondrous without breaking a single law of physics. It reminds us that beauty often hides in the geometry of things, and that in astronomy, even illusions carry meaning. They teach us about the size of dust grains, about the distribution of material, about the timing of ejections and the history of motion. When scientists look at an antitail, they do not merely admire it, they measure it. They decode the angle, the brightness gradient, the contrast against the coma. From these clues, they reconstruct the past motion of the dust, the rotation of the nucleus, and the timing of activity. Well, you see, the antitail of 3I Atlas was not only striking, but also unusually well-defined. Its brightness profile suggested a substantial presence of large grains, grains that had not been blown away in earlier stages of activity. That alone hints at something interesting. It may suggest a nucleus that releases material in bursts or patches, rather than evenly across the surface. It may point to jets that fling out clumps of dust that can settle into the orbital plane. Or it may simply be another sign of 3I Atlas's resilience, its ability to hold on to material longer than similar bodies in our system. And, when sunlight reflects off these heavier grains, the scattering produces a warm, almost golden tone, depending on the grain size and composition. If you imagine that scene through the eyes of the Nordic optical telescope, you might feel as if you are looking at a brushstroke across the firmament, faint but certain, drawn by a hand that understands light better than we do. The anti-tail becomes not just a scientific clue, but a quiet piece of cosmic art. This is where the emotional layer of astronomy deepens, because light is not just photons, it is time made visible. A dust grain catches sunlight that left the sun 8 minutes earlier, and then that reflected light travels for another 2 seconds to reach Earth. In that small delay, light records the motion of ancient particles drifting through the gravity of our star. So when we study an anti-tail, we are reading a delayed story, a story that began long before the photons entered our telescopes. Time becomes a landscape we journey through, not a sequence of ticks on a clock. And once you grasp that, the beauty feels less like confusion and more like revelation. The universe is saying, look at what I can do with nothing more than dust and geometry. Look at how the simplest ingredients can create illusions that make you question what you thought you knew, all without breaking any rules. In earlier comets, astronomers sometimes mistook anti-tails for structural anomalies or breakups, until careful modeling revealed their optical nature. But with 3I Atlas, the effect is clearer because of the alignment with Earth's perspective. It is almost as if the comet passed through the perfect window of visibility, offering us a clean example of the phenomenon. And because 3I Atlas is interstellar, there is a sense that perhaps it wanted to show us something, not intentionally, of course, but by chance, by geometry, by cosmic choreography. Well, perhaps this is where curiosity turns into something deeper, perhaps even philosophical. Because if the anti-tail forms from dust settling along the orbital plane, and if that dust comes from jets that erupt from the nucleus, then the shape of the anti-tail is a kind of fingerprint. It tells us something about the dynamics of the comet, about its rotation, about where the active patches are located, about the size of the grains and the texture of the surface. Every curve of light is a clue. Every faint extension is a whisper from the past. And as we linger with this thought, we begin to see how the phenomenon leads us naturally into the next stage of understanding. Because the anti-tail is not just a trick of geometry, it is also a window into the physical scale of the structure, the distances involved, the way dust spreads across hundreds of thousands of kilometers, the meaning hidden within the sheer size of the visible envelope. So, as we move forward, still walking alongside this interstellar wanderer, the path of dust will draw us onward into the realm of distance and measurement, where even numbers become part of the story, where the scale of the halo and the span of the dust sheet tell us something profound about the physics at play. And there, in that widening perspective, Chapter 3 quietly begins to take shape. Well, you see, as we follow that delicate thread of dust stretching behind 3I Atlas, something begins to shift in our understanding. Up to now, we have been looking at the shape of the anti-tail, the angle, the way light scatters across the orbital plane. But if you stay with the image for a moment longer, if you let your eyes adjust to the faint halo surrounding the nucleus, you begin to sense something else, something about scale, something about the sheer size of the structure that 3I Atlas carries with it as it drifts away from the Sunday. And perhaps this is where the story truly expands, because distance and scale are not just numbers. They are the architecture of the universe, the silent scaffolding that shapes every pattern we see. You know, when astronomers measured the position of 3I Atlas during those observations, they found it was sitting at about 1.43 astronomical units from the Sunday, a little farther out than Earth, but still close enough that sunlight reached it with enough strength to illuminate every grain of dust. And Earth itself was about 2.16 astronomical units away from the comet at the time. That distance may sound large, but in cosmic terms, it is a gentle reach, a closeness that allows telescopes like the Nordic Optical Telescope to resolve the faint textures of the coma. Still, when you imagine the space between Earth and 3I Atlas, you are imagining a gulf of more than 300 million kilometers. Light crosses that gulf in just under 18 minutes. A spacecraft would take months. And yet, through that immense distance, we can watch the subtle glow of dust suspended around a tiny interstellar wanderer that is no wider than a small mountain. This is where the mind begins to stretch a little, because at such distances, the halo of dust surrounding 3I Atlas becomes not just an observational detail, but a landscape in itself. The frame used by the observers covers nearly 500,000 kilometers across. 500,000. That is more than the distance from Earth to the Moon. If you could lay the entire Moon-Earth gap beside the dust cloud of 3I Atlas, the cloud would swallow it whole. And when you think of it that way, the image changes. The comet, that tiny icy body only a few kilometers wide, suddenly becomes the center of a vast kingdom of dust, motion, and faint reflected sunlight. A kingdom large enough to hold worlds, and yet, the nucleus remains almost invisibly small at the center of this immensity. You see, that contrast is part of what makes comets so enchanting. A point of ice and rock, only a handful of kilometers across, can shape a halo tens or hundreds of thousands of times larger than itself. It is like watching a candle illuminate an entire cathedral. The scale is disproportionate, and that is precisely what reveals the physics at work. Because for dust to spread across 500,000 kilometers and maintain its structure, the forces at play must be subtle and persistent rather than explosive. The sublimation must be steady. The ejected grains must be guided by both momentum and sunlight. And in the case of 3I Atlas, perhaps there is something even more interesting happening beneath the surface. Well, as astronomers examined the images more closely, they noticed that the halo was not symmetrical. One side stretched farther, softer, and more gradually, as though the dust were pouring into space along a direction favored by the comet's rotation. The other side showed a sharper boundary, suggesting that certain regions of the nucleus were more active than others. These differences may seem small, but when you extend them across hundreds of thousands of kilometers, they reveal deep truths about the internal structure of the comet. Imagine for a moment a spinning sphere of ice with pockets of volatile material embedded at uneven depths. As it rotates, those pockets release gas at different rates. One region might send material at slightly higher velocity, shaping a longer wing of the halo. Another region might be quieter, producing a sharper drop-off. And, when the halo is this large, even a small asymmetry becomes a giant signature in the sky. It is like tossing a single pebble into a calm pond. The ripples spread outward, and by the time they reach the shore, they are broad and gentle, but their shape still contains every detail of the moment the pebble fell. The dust of 3I Atlas is like that. A faint ripple across space, carrying the memory of the moment it left the surface. What makes this even more fascinating is that distance does not blur the story, it sharpens it. Because the light that reaches us from the dust has traveled millions of kilometers, passing through the vacuum between worlds, it arrives softened but pure. And when scientists analyze the distribution of brightness across the halo, they can infer the size of the dust grains. They can estimate the speed at which they were launched. They can predict how the grains will evolve over time, how they will drift outward, how they will be shaped by solar radiation pressure. Distance, in this sense, becomes a magnifying lens, revealing the subtle dance of physics playing out far from our reach. You know, what I find striking is how numbers like 1.43 or 2.16 astronomical units can seem cold at first, abstract, mathematical. But when we sit with them for a moment, when we let them sink into the story, they gain meaning. They tell us the sun's warmth is still strong enough to evaporate ancient ices at that distance. They tell us Earth sits far enough to see the whole dust structure at once, but close enough to resolve its features. They tell us this comet's halo is not just a simple glow, but a map of forces, motions, histories, and materials, all shaped by millions of years and billions of kilometers of wandering. Perhaps what moves me most is the human side of these numbers. Somewhere in the observatory, a scientist entered the coordinates into a tracking system. Another turned the telescope gently across the sky, nudging it almost imperceptibly to follow the comet's path. Someone saw the first faint smear of light in the image and realized it was not just the nucleus, but the vast dust cloud around it. They were looking not just across space, but across time. The dust they saw may have been released days, weeks, or even months earlier. In a very real sense, observing distance is observing history. And that's the thing. The scale of the dust cloud tells us that 3I Atlas is not merely active, it is persistent. Its activity is not a brief sputter of sublimation, but part of a long, continuous process that has been unfolding for months. For the dust to fill such a large volume, the comet must have been shedding material long before the observations of November the 11th, perhaps even before it reached perihelion. And this raises questions. Did the comet begin venting far out in the solar system? Did it carry volatile compounds that sublimated easily, even in cold sunlight? Or did the heating of the nucleus build up over time until a slow but steady release of dust became inevitable? Well, as we stare at the vast halo of 3I Atlas, we begin to recognize that size is a clue, a subtle, gentle clue. The shape of the halo tells us where the dust came from. The extent tells us how long the activity has lasted. The brightness tells us the density. The asymmetry tells us the distribution of active regions. And the distance tells us how these features scale across space. In astronomy, distance is never just separation. It is context. It gives meaning to motion, direction, and time. You see, when 3I Atlas sits at 1.43 astronomical units from the sun, the sunlight it receives is less intense than what Earth receives, but still strong enough to excite the dust. And when Earth sits at 2.16 astronomical units from 3I Atlas, we see the halo at an angle that allows the anti-tail to bloom. If Earth were positioned differently, if the angle were steeper or flatter, the anti-tail might have been invisible. The entire event, the entire visual effect, depended on a geometry so delicate that even a slight change would alter the result. The scale of space sets the stage for the scene we witnessed. And, this subtle interplay between scale and perception is not just academic, it is emotional. It reminds us that our view of the universe is always shaped by where we stand. That beauty often appears not because something is rare, but because the alignment is perfect. 3I Atlas teaches us that even ordinary dust, released from an icy body only a few kilometers wide, can become something extraordinary when seen across enormous distances. Perhaps this is the point where numbers stop feeling like measurements and start feeling like part of the story's rhythm. The size of the halo, the dust's extension across 500,000 kilometers, the distance from the Sunday, the distance from Earth, all of these values are threads woven together into a larger tapestry. They reveal that 3I Atlas is not just surviving, not just releasing bursts of gas and dust, but painting a sprawling portrait across the inner solar system. And each grain of dust in that portrait tells a story of energy, temperature, pressure, and time. Well, as we lean a little closer into this portrait, the question arises naturally. If the halo is this vast, if the dust sheet extends across such immense space, if the angles align so precisely, then what lies deeper in the structure of 3I Atlas? What does the dust reveal not just about the comet's position, but about its inner workings? Because dust is only the surface. Beneath it lies something more dynamic, jets. Long, powerful jets of gas and dust that erupt from the nucleus and carve great extensions across space. And it is there, in the story of those jets stretching for millions of kilometers, that our curiosity is about to lead us next. Well, you see, as we drift from the gentle haze of the halo into the territory where activity becomes motion, where dust becomes a presenter, flowing river in space, the story of 3I Atlas begins to pulse with a different kind of energy. We have been looking at distance and scale, at the wide, soft glow surrounding the nucleus, at the optical trick of the anti-tail that appears to lean sunward. But if we step just a little closer into the physics of this wanderer, we begin to see something sharper, more dynamic, and perhaps more revealing. Something that whispers not only of dust and geometry, but of forces bursting from deep within the comet's icy interior, jets. Long, powerful jets stretching across millions of kilometers, carving lines through the darkness like streams of breath escaping an ancient frozen lung. And, perhaps the first thing to appreciate is just how astonishingly long these jets really are. Observations made in the weeks around Perihelion revealed something almost surreal. One jet appeared to extend nearly 1 million kilometers in the direction of the Sunday. Another reached even farther in the opposite direction, stretching close to 3 million kilometers outward into space. You know, those numbers are vast beyond intuition. 3 million kilometers is roughly 8 times the distance between Earth and the Moon. Imagine a plume of dust and gas expanding so far that it could wrap around our world many times over and still not reach its end. It is a scale that, once you truly let it sink in, feels almost like myth. But the jets of 3I Atlas are not myth. They are physics. They are the breath of an interstellar traveler, shaped by the warmth of our Sunday. To understand them, we begin with something beautifully simple. When sunlight strikes the surface of a comet, it warms the ice. The ice sublimates, meaning it turns directly from a solid into a gas. And as this gas escapes, it drags dust grains with it, forming a plume that expands outward into space with every passing hour. This is what we call a jet. But with 3I Atlas, the story does not end with the basic mechanism. What astonishes scientists is not the existence of jets, but their persistence and their extraordinary scale. Well, you see, most comets in our solar system produce jets too. They form when pockets of volatile material buried beneath the surface are exposed to sunlight. These volatile pockets might contain water ice, carbon monoxide, carbon dioxide, or other compounds that vaporize when heated. But in those comets, the jets usually span tens of thousands of kilometers, sometimes hundreds of thousands. Rarely do they extend into the millions. And when they do, it often signals an event of significant violence, like sudden fragmentation or explosive outgassing. Yet with 3I Atlas, these extraordinary jets appear not to be sudden outbursts, but rather long-lived structures, almost serene in their continuity. They form not from violent shattering, but from steady sublimation over long periods. This suggests something profound, that the nucleus of 3I Atlas, small as it is, must be capable of releasing material at a rate far higher than what we would expect from a typical comet. And, not just for brief moments. For weeks, perhaps even months. The million-kilometer jet toward the sun and the 3 million-kilometer jet outward suggest a sustained process, one that requires a surprising supply of volatile compounds. You might think of the nucleus as a small mountain of ancient ice, but here, it behaves like a reservoir that simply does not run dry, and that is unexpected. If 3I Atlas were similar to the comets we know, Such intense outflow would erode it quickly, potentially even break it apart. Yet there it remains, intact. And that's the thing. This resilience raises questions. Not small questions, but deep ones. Questions about composition and structure. Questions about thermal conductivity. Questions about the strength of the material that binds the nucleus together. Perhaps 3I Atlas contains ice that sublimates more efficiently than water. Perhaps its matrix of dust and minerals is held together by forces stronger than the porous aggregates we see in solar system comets. Or perhaps it rotates slowly, distributing heat in a way that prevents thermal stress from building too quickly. You know, all of these possibilities hint at a complexity beneath the surface. Something ancient, something shaped in an environment different from the birthplace of comets we know. When scientists examined the brightness gradients within the jets, they noticed something elegant. The material in the Sunward jet declined in brightness more quickly, meaning the dust grains were smaller or more widely dispersed. Meanwhile, the anti-solar jet, the one stretching nearly 3 million kilometers, showed a slower decline in brightness. This suggests the presence of larger dust grains, grains that drift outward more slowly and linger in the flow. In a way, the jets become a timeline. The near jet shows what happened recently. The far jet shows what happened long ago. The nucleus sits at the center like a storyteller speaking two different languages at once. Well, imagine standing near that nucleus, if such a thing were possible. The surface beneath your feet would be rough, fractured, uneven, but also strangely serene in the vacuum of space. Beneath you, pockets of volatile ice would be simmering, heated by the distant Sunday. Thin cracks would hiss as gas escapes. And from one region, a plume of dust would rise slowly at first, then accelerate as it entered space. It might look like smoke from a campfire in the windless night, curling outward in a great arc. And if you step to another region, another plume might be streaming outward in the opposite direction, shaped by the rotation of the comet and the angle of sunlight. These plumes would not roar or rumble. They would simply expand in majestic silence, carving their way across millions of kilometers. And, the silence is important, because when we picture jets, we sometimes imagine violent eruptions. But in the vacuum of space, there is no sound. Everything unfolds with a kind of cosmic stillness. The jets of 3I Atlas are rivers of gas and dust drifting outward in silence, carrying with them fragments of a world formed elsewhere. This silence, stretching across millions of kilometers, makes the jets feel almost like thoughts, thin and extensive, drifting gently into the void. What fascinates scientists is how well the jets maintain their structure over such immense distances. The regular tail of a comet, pushed away by solar radiation pressure, gradually curves and disperses. But jets often maintain coherence because they originate from specific points on the nucleus. They have direction, momentum, and geometry. And in the case of 3I Atlas, the consistency of direction reveals something about the rotation of the comet. If the jets had shifted or flickered erratically, we might assume that 3I Atlas rotates chaotically. But the long, straight extensions of dust imply a rotation that is either slow or stable, or perhaps both. This means the nucleus likely turns in a gentle, steady rhythm, exposing the same regions to sunlight in predictable patterns. Well, that stability also contributes to the persistence of the jets. As certain regions warm during rotation, they emit gases at a steady rate. And because the rotation does not whip the jets into spirals or alter their direction dramatically, the plumes maintain a clean trajectory through space. This is part of why the anti-solar jet reaches such extraordinary lengths. It does not curl or collapse into turbulence. It drifts outward in a long, straight line, carrying dust farther and farther into the emptiness. And there's another element that shapes these jets: solar wind. The constant flow of charged particles streaming from the sun interacts with the gas in the jets, pushing on it, sculpting it, sometimes bending it into delicate forms. With 3I Atlas, The sunward jet is affected more strongly by this wind, which may explain why it appears thinner and shorter than the anti-solar jet. The outward jet, shielded slightly by the nucleus, encounters less direct solar wind pressure and therefore extends farther. The contrast between the two jets becomes a kind of cosmic compass, pointing toward the sun and away from it, telling us about the forces at play on both sides. And as we place all these elements together, the picture begins to feel almost alive. Not alive in the biological sense, but alive in the sense of movement, structure, and evolving complexity. 3I Atlas becomes more than a wandering rock. It becomes a dynamic system, a system that responds to heat, that releases ancient material, that shapes jets stretching across the solar system. And beneath it all lies a quiet mystery. Why has the nucleus not broken? Why does the material hold? Why do the jets extend so far without tearing the body apart? Perhaps the answer lies in the internal composition, in the density of the people waiter, aggregates that bind the nucleus. Perhaps interstellar comets form differently, linking dust grains in patterns more robust than the fluffy structures of local comets. Or perhaps 3I Atlas is a fragment of something larger, something that once orbited a distant star in a stable environment. When that system encountered a disturbance, 3I Atlas may have been ejected intact, carrying with it the durability of its birthplace. Or maybe, just maybe, there is something about the path between stars that hardens a body. The long, cold journey, the slow sweep through cosmic rays, the silent pressure of micro-impacts, the gradual erosion of weak material. What remains after millions of years drifting between suns might simply be the strongest core. Well, you see, the jets raise questions that echo into deeper layers of understanding. Questions about energy, questions about sublimation rate, questions about the balance between radiation pressure and gravity, questions that lead us into the very part of the physics that governs comets. And this is where the story naturally shifts into the next chapter. Because if jets stretching millions of kilometers demand such intense and persistent activity, then the next question becomes simple and profound. Where does all that energy come from? Well, you see, when we begin to follow that question of energy, we find ourselves standing at the threshold of a puzzle that feels as vast as the comet's 3 million-kilometer jet. Because those jets, drifting through the darkness with that calm, unbroken persistence, are not just streams of dust. They are manifestations of power. Quiet power? Yes. But power on a scale that forces us to rethink what a small, icy body is capable of. And perhaps this is where the story of 3I Atlas becomes something more than observational astronomy. It becomes a meditation on energy itself, on how heat from a distant sun can unlock ancient depths and release material at rates that challenge everything we assumed about comets. After observing the immense length of the jets, Avi Loeb and others began to ask a simple but profound question. If the jets stretch millions of kilometers, and if they persist for weeks or months, then how much material must be escaping from the nucleus? And more importantly, how much energy does it take to sustain that escape? When scientists estimated the mass being launched into space, the result was staggering. Nearly 5 billion tons of material per month. 5 billion tons. Imagine the weight of mountains being quietly lifted into space, grain by grain, in absolute silence. And yet there it is, drifting away from 3I Atlas like a veil unspooling into infinity. Well, sublimation is an energy-hungry process. To turn ice into gas, the comet must absorb heat. For carbon dioxide ice, that process requires roughly 600 joules per gram. That means that turning 1 kilogram of CO2 ice into gas demands 600,000 joules. And, if the comet truly releases billions of kilograms each day or week, the energy cost becomes astronomical. Loeb calculated that the total energy needed to sustain the jet activity over a month would be on the order of 3 times 10 to the 18 joules. It is a number so large that it begins to lose meaning until we compare it to something familiar. If we imagine that amount of energy as sunlight, and we spread it across a surface, the comet would need to absorb an enormous amount of solar radiation to provide it. But at its perihelion distance, the sun delivers only about 700 joules per square meter per second. So, to supply the energy required for all that sublimation, the comet would need more than 1,600 square kilometers of active absorbing surface. 1,600 square kilometers. That is larger than many cities on Earth. And yet the comet's nucleus, when measured by Hubble, is only about 5.6 kilometers across. A tiny world, smaller than many mountains, yet seemingly producing the energy output of a much larger object. You know, that mismatch is where the questions begin to deepen, because something does not quite add up. If 3I Atlas is really only a few kilometers wide, how can it gather enough sunlight to sublimate billions of tons of material? Where does the energy come from? Is the structure of the nucleus different from what we assume? Could there be deep thermal reservoirs that store heat? Could internal processes amplify sublimation? Or is there something about its composition that changes the calculation? Well, one possibility is that the surface of 3I Atlas is not uniform. Perhaps it contains patches of extremely volatile material that require far less energy to sublimate than we expect. Perhaps these patches are positioned in such a way that they face the sun for long periods during rotation, allowing them to warm continuously. But even then, the numbers remain challenging. Volatile patches alone cannot fully bridge the gap between the required energy and the energy available. Another possibility is that only a tiny portion of the halo is produced by fresh monthly sublimation. That maybe some of the dust seen in the jets was lifted earlier, far from the sun, and has simply drifted outward over long periods. But this does not explain the observed brightness profile, which suggests ongoing release. Nor does it align with the rate at which the dust density declines along the jet. Those patterns point to continuous activity, not relic material. And, if the sublimation truly is ongoing and intense, then we must consider that the nucleus may not behave like the porous, fragile bodies we are familiar with. Instead, it may have a denser composition or a crystalline structure that stores heat differently. When sunlight warms the outer layer, heat could conduct inward, reaching deeper pockets of ice. Instead of sublimating only the thin surface layer, the heat could penetrate centimeters or even meters into the nucleus, releasing far more gas than expected. In other words, the comet could be using stored thermal energy, not just direct sunlight. But even this hypothesis stretches what we know about cometary material. You see, Loeb's conclusion was not that the physics is wrong, but that the object forces us to re-examine the assumptions we use. Perhaps 3I Atlas contains more energy-rich ices than we expect. Perhaps it has large concentrations of CO2 or CO deeply embedded. Perhaps it is more efficient at absorbing sunlight. If the albedo is extremely low, meaning the surface is dark as charcoal, then it absorbs most of the sunlight rather than reflecting it. This could raise the surface temperature significantly. But again, the problem remains. The area of the nucleus is simply too small. Well, you see, the puzzle grows even more interesting when we consider the timescale. A jet that extends 3 million kilometers does not form in a day. It takes weeks of continuous outflow. During that time, sunlight would rise and fall across the rotating surface. Regions would heat and cool, but the outflow suggests that the comet maintained a steady sublimation rate. This implies either an unusually slow rotation, which would keep the same regions exposed to sunlight for long periods, or an internal structure that distributes heat more evenly than typical comets. If 3I Atlas rotates slowly, the sun could shine on a volatile region for hours or even days without interruption. This would provide a consistent energy source, boosting sublimation and allowing the jet to remain stable. A stable jet, in turn, allows dust to drift outward in a straight line, explaining why the jet appears so long and coherent. In contrast, A fast, rotating comet would scatter jets in spirals, producing a messier structure. The orderly jets of 3I Atlas hint at a gentler rotation, almost a slow cosmic pirouette. And then there is the question of density. If 3I Atlas has a more compact, internal structure, perhaps shaped under pressures different from those in our solar system, then it could withstand the intense forces produced by the jets. A typical comet might fracture under such stress, breaking into fragments or collapsing into a cloud of debris. But 3I Atlas remains whole. This suggests that the physical makeup of the nucleus may be fundamentally different. The dust and ice grains may be bound together more tightly. The pores may be smaller. The aggregate may have been shaped by a different kind of cosmic environment. You know, if we imagine 3I Atlas forming in the outer regions of another star system, or in a dense protoplanetary disk, or in a region with intense radiation from nearby stars, it might have developed a sturdiness that few local comets share. Over millions of years wandering between stars, cosmic rays could further alter its structure, compacting it, reducing its porosity, transforming it into something more resistant to thermal stress. This interstellar heritage could explain why the jets do not tear the object apart. But even with these ideas, the energy question lingers. 3 times 10 to the 18 joules is an immense requirement. The sun delivers energy freely, but 3I Atlas must capture it. So perhaps the surface contains dark organic materials formed through photochemical reactions over millions of years. These materials could absorb sunlight more efficiently. If the albedo is extremely low, perhaps only a few percent, then the energy capture might be higher than expected. And yet, even then, the numbers remain tight. Well, you see, this is precisely why Loeb emphasized that the analysis is not a final answer, but an invitation to re-examine our assumptions. An invitation to consider that interstellar objects may not behave like the icy relics of our own solar system. An invitation to broaden our models of sublimation, energy absorption, and structural integrity. 3I Atlas becomes a question mark, drifting through space. A question that challenges us to rethink what a small body can do under the touch of sunlight. And perhaps this is the philosophical beauty of the problem. Because the universe is not required to fit our expectations. When something does not add up, it is not a failure of nature. It is an opportunity for us to listen more closely, to question more deeply. 3I Atlas may not violate physics, but it may sit in a region of parameter space we rarely explore, a region where density is high, energy absorption is efficient, and sublimation behaves differently. You know, as the jets continue to drift outward, carrying with them fragments of ancient ices, the energy that launched them becomes a silent story told across millions of kilometers. Each dust grain carries the memory of warmth, the memory of the moment sunlight touched the surface, and as we trace the path of those grains, we are tracing the flow of energy through a body shaped by unknown histories. And from here, the next mystery begins to unfold with quiet inevitability. If the energy budget challenges our understanding, then the next step is to look more closely at the physical size of 3I Atlas itself, at the mismatch between what we see and what the energy calculations demand. And that leads us toward a new question, one that begins to rise like a distant light on the horizon. What if the comet is smaller than the energy it needs to absorb? And what does that tell us about the true nature of its surface? Well, you see, when we arrive at this question of size, a kind of quiet tension settles into the story. Because if the energy required to sustain the immense jets of 3I Atlas is as large as the calculations suggest, then something fundamental seems out of balance. It is as if the comet is performing a feat that its small physical form should not allow. And that imbalance invites us to look more closely at the dimensions of the nucleus, to ask whether its size and surface area can really account for the power it unleashes. This is where the narrative shifts from the grandeur of million-kilometer jets to the intimate geometry of a body only a few kilometers wide. A contrast so sharp that it feels almost poetic. You know, when Hubble turned its gaze toward 3I Atlas, what it saw was a nucleus no more than about 5.6 kilometers across. That is tiny in cosmic terms. Smaller than many of the comets we have studied in our own solar system, smaller than the mountains that rise above the clouds on Earth. And yet, according to the sublimation calculations, if 3I Atlas were to absorb enough sunlight to power the energetic jets we see, it would need to have an active area of more than 1,600 square kilometers. To put that in perspective, that is equivalent to a sphere roughly 23 kilometers in diameter, far larger than the 5.6-kilometer object we observe. Well, you see, this mismatch lies at the heart of the puzzle. How can such a small body present the effective absorbing area of something 4 or 5 times larger? How can it gather enough sunlight to sublimate billions of tons of gas and dust each month? The sun does not discriminate. It delivers energy according to surface area. A small object receives only a small stream of light, and yet 3I Atlas behaves as though it possesses a broad, sunlit plane rather than a compact, icy surface. And, perhaps the first thought that arises is whether the nucleus is larger than we think. Could it be surrounded by a dense, unresolved coma that hides the true dimensions? Could its reflective properties mislead our estimations? But Hubble's resolution is precise enough that the nucleus size is unlikely to be off by a factor of 4. Even if the optical data contains uncertainties, it cannot accommodate such a scale. The 5.6-kilometer estimate may shift slightly, but it cannot become 23. So if the nucleus is truly small, then the next possibility is that not all the required energy comes from direct sunlight striking the surface. Perhaps some internal reservoir plays a role. Perhaps heat absorbed earlier, when the comet was closer to the sun, continues to propagate inward and sustain sublimation. But the thermal conductivity of cometary material is usually too low to support such an effect over the required timescales. Heat travels slowly through porous, icy matter. It cannot penetrate deeply enough or rapidly enough to account for billions of tons of sublimation per month. Well, that leads us to consider something subtler. What if the surface of 3I Atlas absorbs sunlight far more efficiently than the surfaces of most comets? What if the albedo is incredibly low, so low that it reflects almost none of the incoming light? Instead, it would swallow the solar radiation like a black stone warming beneath a summer sun. If the albedo were near zero, the surface temperature would rise, increasing the sublimation rate dramatically. And yet, even if 3I Atlas were as dark as charcoal, absorbing nearly all the sunlight it received, the numbers still remain difficult to reconcile. The active area required would shrink, yes, but not enough. The fundamental limitation remains the same. A 5.6-kilometer nucleus simply does not have the surface necessary to gather energy on the scale required. And that's the thing. The more carefully we examine the physical limits, the more the object begins to feel like a contradiction. Not a contradiction in nature, but a contradiction in our model. It is as though 3I Atlas occupies a region of cometary behavior that stretches our assumptions beyond their comfortable boundaries. Perhaps it is not that the object is too small, but that the framework we use to describe sublimation is too simple. You know, if we imagine the surface of 3I Atlas up close, perhaps it does not resemble the smooth, dusty plains we have seen on comets like 67P. Perhaps, instead, the surface is rugged, fractured, filled with deep pits and overhangs that multiply the effective surface area. A surface that is not the simple outer shell of a sphere, but a labyrinth of miniature caverns and fissures. If sunlight were to reach deeply into these cracks, reflecting and scattering within them, the effective absorbing area could increase far beyond the geometric surface. The sun would not simply strike the outer shell, it would fill the interior spaces with light, warming pockets of ice in places ordinary comets would never expose. Well, this idea is not entirely speculative. When the Rosetta mission mapped 67P, it found that the comet's surface was far more complex than expected. Large pits, cliffs, and fractured walls created local environments where sunlight could penetrate deeper than the simple surface geometry would suggest. And yet, 3I Atlas might take this idea to an extreme. If the surface is dramatically fractured, if its porosity is organized in such a way that light reaches layers normally protected, then the effective sublimation area could grow substantially. And consider the possibility that 3I Atlas rotates slowly enough for sunlight to linger over these complex structures, heating them, warming their interiors, triggering sublimation not just at the outermost layer but along walls and channels deeper within. In such a scenario, the comet effectively behaves as though it were several times larger, not in physical size, but in functional area. Light would dance across the inner surfaces of the fractures, scattering into the depths. And the heat, once absorbed, would not easily escape. This could create an internal microclimate where sublimation continues long after the sunlight has moved on. But even this scenario, as imaginative as it is, must contend with the magnitude of the energy required. The difference between a 5-kilometer object and a 23-kilometer one is simply too immense. The cracks would need to expose an extraordinarily large internal surface. The porosity would need to be extreme, and yet, perhaps extreme is precisely what an interstellar heritage produces. You see, 3I Atlas may have formed in an environment drastically different from the icy outer reaches of our own solar system. It may have condensed in a region with higher pressures, or in a disk with different chemical compositions. It may contain exotic mixtures of ices that sublimated at lower temperatures or more efficiently. Some ices require far less energy to vaporize than carbon dioxide. If 3I Atlas contains significant amounts of such volatiles, the energy requirement drops sharply. This possibility is tantalizing because interstellar objects are, by definition, fragments of alien worlds. Their chemistry may not mirror what we see in our local comets. Perhaps the nucleus contains unusual compounds that sublimate with minimal heating, or perhaps the distribution of ices is layered in a way that channels energy into specific pockets, amplifying sublimation efficiency. The idea of exotic ices may sound speculative, but in the vast variety of planetary systems beyond our Sun, chemical diversity is not just possible, it is inevitable. And still, the problem remains. Even if 3I Atlas contains energetically efficient volatiles, the visible jets imply that substantial mass is being ejected. The more efficient the volatile, the more quickly it depletes. Yet the jets persist. This persistence suggests not a thin layer of exotic ice, but large reservoirs. Reservoirs that the comet could have accumulated during its formation, or during its ejection from its home system, or during its long journey through interstellar space. Well, you see, another avenue of thought is that the sublimation may be boosted by processes we rarely consider. For example, thermal fracturing could expose fresh surfaces continuously. As sunlight cracks the outer layers, new volatile material becomes available. In this scenario, the effective sublimation area grows over time, even as the comet moves outward. The jets become self-sustaining, fed by the constant renewal of exposed ice. If this is the case, then the surface we see now is only the latest expression of a long chain of fractures and peelings. The comet could be undergoing a slow, outward curling of its outer shell, revealing fresh layers like pages of a frozen book opening one after another. And each newly exposed page would warm, sublimate, and join the jets. And this model aligns with the idea that 3I Atlas is structurally resilient. If the outer layers crack without shattering the entire nucleus, then the dynamics of sublimation could proceed in a controlled, efficient way. Instead of breaking apart catastrophically, 3I Atlas could evolve gently, the way a block of ice melts along its edges without collapsing. You know, when we step back and look at all these possibilities together, What we see is not a single, clean explanation, but a tapestry of incomplete answers, pieces that hint at a truth we do not yet fully grasp. The mismatch between size and energy forces us to imagine new configurations of matter and heat, forces us to consider how interstellar objects differ from local ones, forces us to confront the limitations of our models. And that is the beautiful thing about these puzzles. They leave us with more questions than answers. They nudge us toward complexity, toward humility. They remind us that the universe is larger, more varied, more inventive than our equations sometimes allow. And as we hold this tension between what we see and what we expect, another question begins to rise gently into view. If the surface is so complex, if the sublimation is so efficient, if the jets are so surprisingly strong, then what does this tell us about the deeper structure of the nucleus? Not just the surface cracks or the absorbing area, but the architecture of the ice itself, the pockets of volatiles, the uneven distribution of activity. And so, almost naturally, almost as though the comet itself were guiding us, the story turns toward those irregular reservoirs beneath the surface, where activity is born and where the next chapter quietly begins. Well, you see, as we linger with that question of size and energy, something deeper begins to stir beneath the surface of the story. Because if the nucleus of 3I Atlas truly cannot absorb enough sunlight across its tiny 5.6-kilometer shell to power the monumental jets we see, then the next place we must look is inward. Not into equations, but into the very architecture of the comet's body, into the pockets of volatile material hidden beneath the crust, into the uneven landscape of buried reservoirs that may pulse and flare when sunlight creeps into the right cracks. And, perhaps this is the point where the comet stops feeling like a simple object drifting through the solar system and starts to feel like a layered, breathing world of its own, imperfect, fractured, ancient, and full of secrets. You know, when we study comets in our own neighborhood, one of the first things we learn is that activity is rarely uniform across the surface. Most of the time, only a few % of a comet's exterior is actively sublimating at any given moment. The majority of the crust is inert, covered by dust and rock that insulate the deeper ices from sunlight. And yet, even within that tiny fraction of active area, the jets can reach impressive scales. If you imagine a comet like 67P, visited by Rosetta, you might picture the small vents and cliffs where sunlight warms exposed ice and gas erupts. These regions behave almost like breathing pores, little chimneys that tell us the surface is alive with change, even if 98% remains cold and still. Well, you see, if this uneven activity is common in local comets, it is almost certain to be true for an interstellar object like 3I Atlas. In fact, the unevenness may be far more dramatic. The comet may contain pockets of ice arranged in strange patterns, shaped not by the calm, steady processes of our own solar system, but by the chaotic infancy of a distant star system with its own storms of dust and gravity. The interior might be a patchwork of ices that formed under different temperatures, trapped beneath the surface in layers that never quite settled into uniformity. And, these internal pockets of ice would behave like little reservoirs, some shallow, some deep, some insulated, some exposed through fractures. Imagine walking across a frozen lake whose surface is dotted with thin ice in some places and thick ice in others. Under your feet, water might press upward, finding the weak point where it can break through. The comet's sublimation works in a similar spirit. The internal pressures change as sunlight heats the surface. Gas builds up, seeping along cracks until it escapes in narrow, powerful jets, not from the entire surface but from these vents that open into specific reservoirs. If 3I Atlas contains many such pockets, and if sunlight reaches them through a maze of fractures, then its effective sublimation area could be far higher than the geometric surface suggests. It would not need to be a uniform 23-kilometer sphere to absorb the required energy. Instead, it could behave like a hollowed labyrinth, exposing internal walls and surfaces to light that penetrates deeper than we expect. You know, this image of internal reservoirs resonates with something we've already seen in comets like Tempel 1, where deep impact revealed stratified layers of different ices, and in 67P, where pits and fractures exposed pockets of volatiles long buried beneath the crust. The lesson from those missions was simple and profound. Comets are not simple piles of ice. They are complex, layered bodies with histories written inside them. Their surfaces are deceptive masks. Underneath lies a world of cavities, conduits, and volatile rich seams. Well, with 3I Atlas, this complexity could be magnified, because an interstellar object may have experienced processes we have never witnessed up close. It may have formed near a young active star where radiation and stellar winds sculpted the ice in unpredictable ways. It may have wandered through warmer regions of its home system before being ejected. It may have acquired fractures through tidal interactions with large planets. It may have lost layers, gained others, and carried the scars of collisions with small bodies in the interstellar medium. And, as sunlight warms the comet now, in the late months of its passage through our solar system, those internal seams of ice could come alive in different rhythms. Some might release gas gently, producing faint halos. Others might erupt in surges, feeding the long jets we see. The pattern of activity may reflect not just the heating from the sun, but the architecture of the interior. If the pockets run deep, sublimation could continue long after the surface cools. If they connect to each other, pressure could build and vent through a single point, amplifying the jet's strength. And if the pockets contain ices of different volatility, the activity could shift as the comet moves farther from the Sunday water might sublimate near perihelion. Carbon monoxide or carbon dioxide might dominate as 3I Atlas retreats into the outer solar system. You see, this mosaic of pockets would allow the comet to sustain activity for long periods, even if the actual surface area is small. A tiny vent might open into a chamber that spans tens or hundreds of meters, and light, bouncing through the fractures, might warm those chambers enough to keep sublimation alive. It is the same principle as warming your hands near a small opening in a cave where heat has built up inside. The warmth that emerges does not reflect the size of the opening, but the volume of the chamber behind it. Well, if 3I Atlas operates under similar principles, then those enormous jets begin to make sense. They become the visible expression of a deep interior filled with volatile, rich cavities. Perhaps sunlight trickles into these pockets through networks of fractures that have grown over hundreds of millions of years. Perhaps the comet's long, quiet journey between the stars allowed microcracks to form slowly, preparing the structure for a sudden awakening when it finally met the warmth of our Sunday. And you know, this paints a picture of 3I Atlas that feels strangely alive. Not alive biologically, but alive in the way geology can be alive. Alive in the way landscapes respond to heat, pressure, and time. Each pocket of ice becomes a story. Each vent becomes a voice. Each jet becomes a signal that something deep within has begun to move again after a silence that lasted longer than the human species has existed. This uneven distribution of activity also explains the visual asymmetry in the halo. Some regions of the comet release dust at higher rates. Others remain still. As the nucleus rotates, these active patches come into and out of sunlight. The rotation may be slow enough that a patch facing the sun stays warm for long periods, feeding the jets with steady pressure. But once it turns away, sublimation slows, pressure drops, and the jet weakens. These rhythms create the complex patterns of brightness we see in the coma. Well, this leads us to one more important point. When only a small fraction of the surface is active, the stresses on the nucleus become uneven. Jets act like thrusters. They push on the comet. If the structure is fragile, these uneven forces can cause fractures. But 3I Atlas appears to hold. This is another hint that the nucleus may be stronger or more cohesive than typical comets. The uneven sublimation should be tearing it apart. And yet it remains intact. And, That resilience is fascinating. It suggests a material strength or internal cohesion that has little precedent in our solar system. If jets emerge from uneven pockets, but the nucleus resists cracking, then the structure must be uniquely robust. Perhaps the ice is interlaced with minerals in a dense, rock-like matrix. Perhaps the porosity is lower. Perhaps the binding forces between grains are stronger. The comet may be less like a loose pile of snow and more like a compressed ancient relic. You see, this combination of strong jets and structural integrity is rare. In comets like Ison, powerful heating near the sun shattered the nucleus. In others, like 2017's Oumuamua, sublimation barely occurred. But 3I Atlas sits in a curious middle ground. It is both unusually active and unusually resilient. This combination makes the internal structure especially intriguing. A comet with uneven pockets of volatile ice should crack under the strain. Yet 3I Atlas holds together long enough to produce jets millions of kilometers long. Well, perhaps the most compelling explanation is that the nucleus contains a heterogeneous interior, regions of dense, cohesive material interwoven with pockets of volatile ice. When sunlight warms the pockets, gas escapes through pathways without collapsing the structure. It is like a sponge filled with frozen gases, strong enough to hold its shape while still releasing material. This is the kind of complexity that interstellar origins could produce. And if pockets of different compositions lie at varying depths, the comet might awaken layer by layer. First, the shallow pockets, then the deeper ones as thermal waves penetrate. The pattern of jets might shift as the comet evolves, and the longer the activity persists, the more the inner architecture reveals itself. You know, as we imagine this internal landscape full of unseen chambers and branching fractures, another question quietly emerges. If the nucleus is so uneven inside, and if sublimation occurs through narrow vents, then how does the structure survive the internal pressures? How does it resist the forces that would tear apart a weaker body? What gives it that resilience? And that, well, leads us naturally into the next phase of the story. Because once we begin to consider the strength of the material and why this interstellar wanderer has not fractured like so many local comets, we find ourselves drawn toward a new mystery. A mystery about the structural integrity of 3I Atlas. A mystery about why it holds together so well under conditions that should overwhelm it. And so, as the jets continue to whisper from their hidden reservoirs, the next question rises softly into the vacuum. If the pockets beneath the surface are so active, then what keeps the comet from breaking? Well, you see, when we step from those hidden pockets of volatile ice into the question of structural integrity, the tone of the story shifts again. It becomes quieter, more contemplative, because now we are facing something that feels almost paradoxical. A small interstellar comet, riddled with internal cavities, fractured by pockets of sublimation, exhaling powerful jets that should by all accounts tear it apart, and yet it continues onward through space, whole and unbroken. And, perhaps this is where we begin to understand that 3I Atlas is not just unusual in its behavior, but in its very essence. That the way it holds together tells a story as deep and strange as its million-kilometer jets. You know, when we look at comets in our own solar system, one of the most striking lessons comes from the Rosetta mission. When the spacecraft approached Comet 67P, it found a body so fragile that entire cliffs crumbled from minor thermal stresses. Cracks opened simply from sunlight, heating the surface by a few degrees. The comet behaved like a loosely bound pile of rubble, its cohesion so minimal that even small jets caused surface collapse. And in many other comets, the mere act of accelerating away from perihelion is enough to split them into fragments. Some disintegrate completely, some shed layers, some vanish into diffuse clouds of dust, their nuclei erased by the sun's heat. Well, you see, that fragility is what makes 3I Atlas so mysterious. Because with jets far more powerful than those seen in many solar system comets, with sublimation rates far higher, and with a structure apparently filled with uneven pockets of volatile ice, the expectation should be simple. 3. I-Atlas should break. It should crack under the strain. It should fracture into smaller bodies. Its rotation should wobble under asymmetric thrusts. Yet none of this seems to be happening. 3. I-Atlas continues through its orbit not as a cloud of remnants, but as a single coherent nucleus. And, that coherence is not just surprising. It is genuinely challenging. It forces us to ask what physical processes might allow an interstellar object to endure forces that would easily overwhelm one formed under the gentle conditions of our own outer solar system. Perhaps the material strength of 3I-Atlas is higher. Perhaps the nucleus is held together by more robust bonds between dust and ice grains. Perhaps its internal porosity is lower. Or perhaps, in the simplest and most humbling interpretation, comets formed beyond our sun possess a diversity of structures we have barely begun to imagine. You know, if we picture the nucleus up close, perhaps it will help us sense what might be happening. Imagine standing on the surface of this small world, surrounded by a landscape of fractures, ridges, and vents. Beneath your feet, pockets of volatile material are releasing gas. Jets rise from narrow openings like geysers in a frozen desert. In a solar system comet, this would create stress lines. Tension would build in the brittle crust. Cracks would widen along planes of weakness. But 3I-Atlas stands firm. The jets erupt, the pockets empty, but the overall structure remains intact. It is as if the comet has a skeleton of its own, a frame that supports the surface against collapse. Well, what could form such a skeleton? One possibility is density. If 3I-Atlas is denser than local comets, with less empty space inside, then the material would be more resistant to fracturing. In typical comets, up to 70 or 80% of the interior can be void space, a structure that porous behaves almost like a snowbank. Pressured from within, it collapses. Heated from above, it cracks. Dust grains drift apart with little resistance. But if the porosity of 3I-Atlas is lower, if the grains are packed more tightly, if the ice binds to the minerals with greater cohesion, then the forces generated by sublimation may be insufficient to break it. The comet would act more like a solid object and less like a fragile aggregate. And, this idea connects naturally to the comet's interstellar origin. For local comets, low density results from gentle accretion processes in the cold outskirts of the solar system. Dust grains stick together lightly, forming loose assemblies. But in another star system, conditions might differ dramatically. The protoplanetary disk might have been denser. Ices might have formed under higher pressure. Dust grains might have fused together into stronger aggregates. Minerals might have crystallized differently under the influence of nearby stars or shock waves from stellar formation. 3. I-Atlas could carry within it a structure forged in a harsher nursery, strengthened before it ever left home. You know, we sometimes imagine interstellar objects drifting serenely through the void, untouched by time. But the reality is harsher. The space between stars is filled with radiation. Cosmic rays bombard objects continuously. Over millions of years, this radiation can alter materials in subtle but profound ways. Surface layers may harden, ice may chemically transform, weak grains may crumble, leaving only the stronger bonds intact. Bit by bit, the crumbly parts of the comet might be eroded away, leaving behind a more compact core. In this sense, the long journey itself becomes a sculptor, chiseling away at the fragile parts and reinforcing the stronger ones. Well, if 3I-Atlas has undergone such treatment over eons, what remains today may be the most resilient version of its original form, a core that has survived the harshest environments imaginable, a body hardened by radiation, by cold, by collision, and by time. When jets erupt from such a structure, they may strain it, but not enough to break it. The strength of the remaining material could be orders of magnitude higher than what we expect from solar system comets. And, there is also the matter of how the internal pockets are shaped. If they are distributed in a way that diffuses pressure, then the forces exerted by sublimation would spread more evenly. Pressure that builds up in one pocket might escape through multiple channels, reducing the stress on any single fracture. Instead of one large cavity acting like a balloon ready to burst, 3I Atlas might contain a network of smaller chambers, each venting independently. This would allow the comet to endure intense sublimation without rupturing. But there's something else, something more subtle, that might contribute to 3I Atlas's resilience. Its rotation. If 3I Atlas rotates slowly, then the heating of its surface occurs gradually. Regions that come into sunlight warm gently before rotating out again. This prevents the kind of rapid thermal spikes that cause cracks in more fragile comets. A slow rotation acts like a buffer, smoothing the temperature gradients that would otherwise strain the surface. And if the comet's rotation period is stable, without tumbling or chaotic motion, then the active regions remain predictable, producing thrusts that do not destabilize the nucleus. Rotation plays a larger role in comet survival than we often realize. Many comets fragment because asymmetric jets alter their rotation, shifting angular momentum until the nucleus begins to wobble. The wobble increases internal stress, leading to fractures. If 3I Atlas is resistant to such changes, perhaps because of its internal structure, then it avoids this fate. The jets may push it gently, but the nucleus remains steady, absorbing the forces without tearing. Well, all of this paints a picture of a comet that is not fragile, but robust. A comet that stands in contrast to the ones we have touched or observed up close. And that contrast invites a deeper philosophical question. What does it mean for a comet to be strong? Not strong in the human sense, but strong in the cosmic sense. Strong enough to cross the cold gulf between stars. Strong enough to survive a perihelion passage. Strong enough to endure the violent exhale of million-kilometer jets. That strength is not accidental. It is the product of origins we do not yet fully understand. And, perhaps this is exactly why Avi Loeb emphasized that 3I Atlas defies expectations. It is not simply that the jets are long or that the nucleus is small. It is that the structure holds under conditions where, in our existing models, it should fail. That resilience is a clue that 3I Atlas may belong to a different class of objects altogether. A class shaped by processes beyond the familiar, by physics that remain within our understanding but stretch toward its edges. This raises another possibility. If the nucleus is stronger, then perhaps the forces generated by the jets are actually lower than they appear. The mass flow rate could be high, but the pressure differential small. Gas might seep through porous channels, releasing material without building destructive pressure. In this interpretation, the comet does not resist the jets. The jets simply never apply significant stress. The structure remains intact not because it is unbreakable, but because the forces trying to break it are gentler than the surface brightness suggests. However, that interpretation would require that the jets consist mostly of low-velocity flow, which does not fully match the observed large-scale extensions. So the truth may lie in between. A strong nucleus, yes, but one that also possesses a sophisticated network of conduits distributing pressure. Well, as we keep turning these possibilities over in our minds, a new question forms quietly at the center. If 3I Atlas is structurally resilient, if it contains deep pockets of ice, if it resists fragmentation under intense heating, then how does this compare to the behavior of comets we know well? Where does it fit on the spectrum of cometary activity? Does it resemble any object we have encountered before, or does it stand alone as a representative of something new? And that question, gentle but persistent, leads us naturally into the next chapter of the story, a chapter where we place 3I Atlas beside Hale-Bopp, Encke, 67P, and others. A chapter where we ask what this interstellar visitor reveals when measured against the familiar bodies of our own solar system. Well, you see, when we begin to place 3I Atlas beside the comets we know well, something shifts in the atmosphere of the story. It becomes less about the object itself and more about the landscape of expectations we carry from our own solar system. Because comets like Hale-Bopp, Encke, and 67P have taught us certain patterns, familiar rhythms, the way a comet brightens as it approaches the sunday, the way jets flare unpredictably, the way the nucleus fractures under heat, the way dust streams form broad, soft arcs that slowly disperse into the solar wind. And, perhaps because we know these behaviors so intimately, because we have centuries of observations and even spacecraft encounters with them, we instinctively compare any new comet to the old archetypes. It is just human nature. We anchor the unknown to the known. But when we place 3I Atlas in that familiar lineup, the Angest DE, comparisons do not fit neatly. Instead, they cast long shadows of surprise, reminding us that interstellar objects carry histories entirely alien to our experience. You know, take Hale-Bopp, one of the most iconic comets of the 20th century. It was large, bright, and full of volatile ices. Yet, even Hale-Bopp, with its impressive activity, displayed behavior that aligned with what we expect from solar system comets. Its jets were strong, but not impossibly long. Its mass loss was significant, but not inconsistent with the size of its nucleus. And its structure, though complex, held together under physical stresses we could model and understand. There was nothing in Hale-Bopp that defied the fundamental physics of sublimation or structural integrity. Well, when we look at 3I Atlas, we see something more extreme. Jets stretching millions of kilometers, a nucleus that remains intact even under sublimation forces that should tear a typical comet apart, a dust production rate that challenges the energy budget of a 5.6-kilometer object. Hale-Bopp was dramatic. 3I Atlas is perplexing. And then we have Encke, a short-period comet that passes near the Sun every few years. Over time, Encke has steadily eroded. Each perihelion strips away more material. Its activity declines. Its surface darkens. Its jets weaken. The comet ages visibly, wearing down in predictable steps. Many comets follow this slow fade. Activity decreases as volatiles deplete and dust layers thicken. It is almost like a heartbeat gradually becoming quieter. 3I Atlas, however, shows no sign of such exhaustion. Its jets are not the gentle sighs of an aging comet. They are the powerful exhalations of something that behaves as though it has deep reservoirs of volatile ices untouched by billions of years of radiation and cosmic erosion. It is as if 3I Atlas arrived in our solar system with a youthfulness that defies the immense time it must have spent wandering between the stars. And, consider 67P, the comet visited by the Rosetta spacecraft. Its structure was fragile, riddled with cracks, prone to collapse. Jets carved new fractures into its cliffs. Thermal stresses split boulders. Dust layers slumped and slid. The surface responded to heat in ways that showed just how delicate cometary bodies can be. Rosetta witnessed this fragility in astonishing detail. 67P survived its perihelion passages, yes, but not without visible wounds. Its surface changed dramatically over only a few months. Well, compare that with 3I Atlas, which sailed through perihelion still intact, still cohesive, still capable of producing long and steady jets. If 67P is fragile pottery, then 3I Atlas feels more like carved stone, not invulnerable, but far more resilient than the comets we have studied up close. And that resilience, that refusal to crumble under pressure, is part of what makes 3I Atlas so striking. You know, when we place all of these comets side by side, we see a pattern. Local comets fit comfortably within the boundaries of behavior we expect. Their compositions, their sublimation rates, their structural weaknesses, their jets, their fragmentation events, these all align with the environments in which they formed. Their stories emerge from disks of dust and ice around young suns. Their structures reflect the physics of slow accretion, gentle collisions, and billions of years spent orbiting within the same gravitational system. 3I Atlas, on the other hand, carries none of those guarantees. It formed somewhere else, around another star, in a protoplanetary disk that may have been denser or more turbulent, in a region where pressure, temperature, composition, and radiation varied wildly from the conditions in our outer solar system. It was shaped by forces we have never observed directly. It cooled under a different sky. It was compressed under different gravitational tides. Its frozen layers remember a history that no Earth-based instrument has ever sampled. And, that foreign history may be the key, because when an object arrives from interstellar space, it is like finding a seashell on a mountaintop. It does not belong to the local geology. It carries stories from an ocean long vanished or far away. 3I Atlas is such a shell, a fragment from another world that crossed unimaginable distances to drift through our sun's domain, and its behavior reflects that difference. When we compare its jets to those of Hale-Bopp or Encke, we see not a familiar pattern, but an amplification, a scale that exceeds what we expect. When we compare its resilience to 67P, we find not fragility, but fortitude. And when we look at the internal activity inferred from its dust, we sense a complexity that goes beyond anything observed in a solar system comet. This leads us toward an idea that is both exhilarating and humbling, that 3I Atlas might represent a category of cometary bodies that formed under conditions different enough to produce material strength, volatile distribution, and sublimation behavior that fall outside our local experience. Not outside physics, of course, but outside the narrow slice of astrophysical environments we have studied in detail. It is as though 3I Atlas is whispering that the diversity of icy bodies in the galaxy is far richer than the small sample we have encountered. Well, this comparison also raises important subtleties. For example, while Hale-Bopp had an extended envelope of dust, its jets were broad and somewhat chaotic. 3I Atlas's jets, by contrast, are narrow, coherent, and astonishingly long. This coherence suggests something unusual about the vent geometry or the internal pressure dynamics. Encke loses mass steadily and predictably. 3I Atlas appears to lose mass at explosive rates, yet remains intact. 67P developed fractures from mild heating. 3I Atlas seems almost unfazed by intense sublimation. And, even the antitail seen after Perihelion places 3I Atlas in contrast to familiar comets. Antitails do occur occasionally, but rarely as dramatically or as cleanly as the one imaged in November. The nearly perfect alignment between the dust sheet and the sun's direction created a visual signature more often seen in diagrams than in actual data. These subtle distinctions accumulate, each one small, but together forming a pattern that robustly suggests 3I Atlas is an outlier. But the truly fascinating part of this comparison is not that 3I Atlas behaves differently. It is that it behaves differently in multiple ways at once. It is resilient, yet explosively active. Small, yet energetically powerful. Old, yet behaving as though it contains fresh, unprocessed volatiles. It is like meeting a traveler whose face shows the weathering of a long journey, yet whose voice carries the clarity of youth. And that brings us to a deeper philosophical reflection. When we rely too heavily on familiar examples, we risk narrowing our view of the universe. Hale-Bopp, Encke, 67P. These are points on a map, not the boundaries of it. They tell us what comets can be here, not what comets can be everywhere. In comparing 3I Atlas with these objects, we are not finding contradictions. We are discovering how limited our sample is, how little of the galaxy's diversity we have actually touched. Well, This realization opens the door to a broader perspective. If 3I Atlas is different, then perhaps it is not the exception. Perhaps our solar system is merely one configuration among countless others. Perhaps the comets we have studied are only a sliver of what frozen bodies across the Milky Way can become. And if this is true, then interstellar objects are not curiosities. They are emissaries, messengers carrying data from distant environments. Each one contributes a piece of the puzzle, enriching our understanding of planetary formation across the galaxy. You know, Avi Loeb has suggested repeatedly that interstellar objects challenge our assumptions not because they are anomalous, but because our observational history is shallow. We have so few examples: Oumuamua, Borisov, 3I Atlas. These are not enough to generate robust statistical patterns. It is like trying to describe an entire forest after seeing only 2 or 3 trees. And, if 3I Atlas represents a new kind of comet with higher structural cohesion or more efficient volatile retention, then this might change how we interpret future interstellar visitors. We may begin to expect greater diversity. We may refine our models to accommodate material strength beyond what solar system comets exhibit. We may realize that interstellar comets tell us not what is typical, but what is possible. Well, as we take all of this in, the question that drifts forward, soft and persistent, is this: what else might interstellar comets reveal once we learn to read them properly? If 3I Atlas differs from Hale-Bopp and 67P, then perhaps the next visitor will differ from 3I Atlas. The diversity may be wider than we imagine, and that, leads us gently into the next chapter. Because if interstellar objects carry within them the fingerprints of their home systems, then understanding their nature requires us to look outward toward the stellar nurseries in which they form, toward the dust-filled disks surrounding young suns, toward the environments that sculpt their icy bodies in ways alien and beautiful. And so the story continues, unfolding toward the origins of these wanderers, toward the cosmic forges that craft them long before they set sail across the abyss. Well, you see, when we begin to trace 3I Atlas back toward its birthplace, the story stretches far beyond the narrow corridor of our solar system. It drifts outward, into the great star-forming regions of the galaxy, into the swirling cradles where dust, ice, radiation, and gravity weave the first fragile architectures of worlds. And, perhaps this is where our curiosity naturally leads us. Because if 3I Atlas behaves so differently from Hale-Bopp or 67P, then its origin must lie in environments that sculpted it under rules and pressures alien to anything our sun has ever known. If you imagine the earliest moments of a star system, the image that often comes to mind is a broad, faintly glowing disk swirling around a young star. But the reality is far more dynamic. The birthplaces of stars are violent. They are thick with dust, hot with radiation, crisscrossed by shock waves from nearby supernovae, and stirred by gravitational tides that tug at the material like invisible hands. It is in these chaotic nurseries that planets, asteroids, and comets begin to take shape. Tiny grains of ice collide, dust clumps thicken, fragments combine, break, recombine. And amid this whirl of collisions and accretions, some objects form quickly, some slowly, and some emerge with properties we have barely begun to imagine. Well, you see, our own comets formed in the gentle outer disk of the solar system, where temperatures were low and collisions were soft. That produced loose aggregates, fragile and porous, rich in ices but weak in structure. But if 3I Atlas formed in a region where pressure was higher or where ice and dust experienced stronger gravitational compression, then its internal cohesion could be entirely different. The grains might have fused more tightly. The ice might have crystallized in denser phases. The volatile layers might have settled into deeper pockets under the weight of overlying material. In such an environment, a comet like 3I Atlas might develop a robustness that no solar system comet possesses. And, then there's the radiation. In star-forming regions where massive stars burn hot and bright, ultraviolet light can flood the disk. High-energy photons strike ice grains, breaking molecules apart, rearranging them, creating complex organic residues that deepen the color and lower the albedo of the surface. These photochemical products can make the comet darker, more absorptive, more capable of warming rapidly when exposed to sunlight. A darker surface could, in theory, help explain the higher sublimation rates we see in 3I Atlas. It would soak up energy efficiently, even at large distances from the sunday. Its surface could behave less like ice and more like charcoal, converting even faint sunlight into heat. You know, another intriguing aspect is the possibility that 3I Atlas formed in a disk with different chemical abundances. Each star, after all, forms from a cloud with its own mix of elements. Some disks have more carbon monoxide, some contain more methane, some have higher carbon to oxygen ratios. If 3I Atlas originated in a disk rich in highly volatile ices or compounds that sublimate easily at lower temperatures, then its activity near perihelion begins to make sense. It would not rely solely on water ice to power its jets. Instead, carbon monoxide or nitrogen-based volatiles might dominate the sublimation process, releasing vast amounts of gas even at relatively modest temperatures. And that could help explain why the jets stretch so far, why the dust is accelerated so powerfully, why the comet maintains activity long after passing its closest point to the sunday. Well, this idea opens up a beautiful possibility. That 3I Atlas is not unusual at all within its home system. That it is simply a typical product of a very different stellar nursery. That the behaviors we see as alien or extraordinary might be commonplace in another part of the galaxy. In that sense, 3I Atlas becomes a messenger. Not a one-in-a-million anomaly, but a representative of a family of icy bodies forged under conditions foreign to our own. And, if we zoom out even further, beyond the protoplanetary disk, we begin to see another layer of the comet's journey. At some point in the early history of its home system, gravitational interactions must have flung 3I Atlas outward. Perhaps a giant planet migrated through the disk, scattering comets into deep interstellar space. Perhaps a passing star disturbed the outer cloud, ejecting objects into the void. Or perhaps the entire system shook under the influence of a stellar encounter, sending thousands of icy fragments on long, lonely journeys between the stars. This process, though dramatic, is common. Our own sun likely ejected countless comets during its youth. And so, across the galaxy, billions of icy bodies are thrown into interstellar trajectories every year. Most wander forever in silence. But some, like 3I Atlas, eventually drift close enough to another star that they are captured for a brief, luminous moment. They light up, they sublimate, they whisper stories of their origins. You know, what fascinates me is the sense of time embedded in these journeys. 3I Atlas may have traveled for hundreds of millions of years before reaching our sunday, long before the first forests rose on Earth, long before the continents took their present shape, long before mammals or birds or humans. It drifted through interstellar space, cold and slow, half asleep in the deep dark. And then, in just a few months, it awoke beneath our sunlight, revealing structures and behaviors shaped across cosmic epochs. This long, quiet journey could have transformed the comet in subtle ways. Cosmic rays, for instance, penetrate deep into icy bodies. Over millions of years, they can alter the molecular structure of the ice. They can harden the crust. They can produce exotic compounds that do not form easily within the solar system. They can lower the porosity of the material. And these slow transformations might help explain the resilience of 3I Atlas. A comet sculpted for eons by radiation would naturally develop a robust outer shell, one capable of withstanding sudden heating during perihelion. Well, you see, another part of the story lies in the potential for catastrophic events in the comet's home environment. Interstellar comets may form in systems with highly eccentric, giant planets. These planets could violently scatter icy bodies, causing collisions that compress the interior or fracture it into dense, interlocking pieces. If 3I Atlas originated in such a chaotic region, then its internal structure could be more compact, more crystalline, or more strongly bonded than local comets. It could be the fragment of a larger body, broken during a collision, but retaining a strong, cohesive core. And, if we imagine 3I Atlas as a shard rather than a primordial object, then its unusual behavior begins to feel almost inevitable. A fragment carved by violence would carry a strength far greater than that of a gently accreted comet. It would be like a piece of glass compared to a snowflake. Both are delicate in their own way, but one resists pressure far better. You know, one of the most poetic aspects of this idea is that 3I Atlas may carry within it the memory of a world that never formed. Fragments like this could be the remnants of failed planets, pieces of embryonic bodies that broke apart before they could grow large. In that sense, 3I Atlas could be the fossil of a planet that almost was, an echo of a world that never came to be. Well, as we let that idea settle, the philosophical dimension of the story becomes clearer. Interstellar objects are not simply icy bodies, they are time capsules. When they enter our solar system, they bring a piece of another star's history with them, a history that spans billions of years and countless cosmic events. When we observe an object like 3I Atlas, we are not just studying a comet. We are reading the geological record of a distant dawn. And, the beauty of this realization is that it places our own solar system in a wider context. We see that our icy bodies are only one variation in a much larger spectrum of possibilities. That the architecture of other systems may produce comets with different compositions, different densities, different internal structures, and different behaviors. 3. I Atlas is a reminder that the universe is not obligated to reflect our expectations. It is larger, more varied, more inventive than that. You know, this diversity is what makes interstellar visitors so precious. Every one of them, from Oumuamua to Borisov to 3I Atlas, expands the boundary of what we consider normal. They are the emissaries of distant forges, carrying the fingerprints of their birthplaces. They teach us that the conditions that shaped our solar system are not universal, that the story of planetary formation is richer and more textured than our small sample can show. Well, as we stand here, contemplating the origins of 3I Atlas, we begin to sense the next question rising gently from the horizon of our curiosity. If interstellar comets represent environments far beyond our experience, then how should we approach the anomalies they present? How should we interpret behavior that does not fit neatly within familiar models? What attitude should we adopt when the universe presents us with something that feels both wondrous and puzzling? And so, with these questions lingering softly in the dark, the story moves forward, carrying us toward the next reflection, the importance of scientific humility and what it means to hold wonder and skepticism in the same quiet breath. Well, you see, when we arrive at this chapter, something softens in the way the story breathes. Because up until now, we have been mesmerized by the strangeness of 3I, Atlas, by the quiet defiance in its behavior, by the way it keeps challenging our familiar patterns. But here, in this moment, the mood shifts from curiosity to something like reflection, something like a reminder that science, for all its equations and measurements, is also a human endeavor. A conversation between our expectations and the universe's gentle corrections. And, perhaps this is exactly the place where a kind of humility begins to take root. You know, when Avi Loeb described 3I Atlas as an object that defies expectations, he didn't mean that it violates physics. He meant that it violates us, our assumptions, our models, our instincts about how icy bodies behave. And in science, that moment is precious, because a model that cannot bend eventually breaks, while a model that bends grows wiser. 3I Atlas, in its quiet, drifting way, invites us to bend? Well, you see, one of the recurring patterns in scientific history is that anomalies often precede understanding. They appear as small irritants at the edge of accepted theory, an unexpected orbit, a strange spectral line, a particle behaving just a little differently. At first, these anomalies feel like mistakes, measurement errors, imperfect data. But then, when they persist, they begin to whisper something deeper. They tell us that the universe is nudging us toward a new kind of seeing, a more expansive frame, a better question. 3. I, Atlas, plays that role beautifully, not by contradicting physics, but by reminding us that physics is always provisional, that our theories are maps, not the territory. And you know, there is a kind of grace in recognizing this, a kind of calm that settles in when we stop insisting that nature conform to our expectations, and instead let our expectations evolve in response to nature. And perhaps the most important lesson here is that anomalies demand patience, real patience. Not the hurried rush of trying to force an explanation, but the slow, contemplative patience of gathering more data, refining models, and waiting for patterns to emerge. 3. Atlas is still young in our collective understanding. We have only a handful of images, only a thin stream of measurements, only a small window into its behavior. To leap to conclusions would be premature. To dismiss its oddities would be equally unwise. You see, this is where scientific caution becomes an act of respect. Respect for the data, respect for the unknown, respect for the possibility that the universe is trying to tell us something subtle. 3. Atlas might not require new physics, but it might require new nuance, new sensitivity, new appreciation for the diversity of icy bodies formed in the far reaches of the galaxy. And well, when we consider how rare interstellar objects are in our observational history, the need for caution becomes even clearer. We have only seen a few: Oumuamua in 2017, Borisov soon after, and now 3 Atlas, 3 interstellar visitors in the span of a human decade. Before that, none we could confidently identify. With such a small sample, statistical certainty is impossible. Yet at the same time, each object enriches our sense of what is possible. Each one expands the silhouette of our understanding. You know, Oumuamua itself taught us an important lesson about caution. Its non-gravitational acceleration puzzled many. Some proposed exotic explanations. Others pointed to more mundane mechanisms: outgassing, thermal effects, shape-driven radiation pressure. The debate was vigorous, sometimes heated, but in the end, what became clear was that the object was simply too far, too faint, and too fleeting for definitive answers. And that is not a failure. That is the boundary between knowledge and mystery. 3 Atlas stands in a similar boundary. Its jets stretch farther than expected. Its mass loss seems too high. Its nucleus appears too small for the energy it emits. But these observations, while striking, are not yet complete. They are pieces of a mosaic whose full shape has not emerged. And the role of science here is not to fill in the missing tiles with guesswork, but to wait for the mosaic to grow, to let the pattern reveal itself. Well, you see, it is not just the scientific community that benefits from this humility. We, as observers, as wanderers beneath a curious sky, also gain something from it, because humility in the face of cosmic mystery is its own kind of wonder. It invites us to stay open, to marvel, to say, with a quiet breath, I do not know yet, but I want to learn. And in that gesture, we become students of the universe rather than its critics. You know, one of the most powerful things about astronomy is that it forces us to widen our sense of scale, to think in light years, in millions of kilometers, in time spans that dwarf our lives. And when we do that, when we allow ourselves to feel those scales, a natural humility arises. Not a humility that diminishes us, but one that deepens us. It tells us that the universe is vast, but not indifferent. It invites our curiosity. It welcomes our questions. It rewards our patience. And, 3i Atlas is a perfect example of this invitation. Every anomaly in its behavior is a doorway, not a wall. Every contradiction is an opportunity. Every unexpected observation is a chance for refinement. If the mass loss seems too high, perhaps our sublimation models are too simple. If the nucleus seems too small, perhaps its effective absorbing area is larger than we assume. If the jets are too long, perhaps the internal geometry is more complex. Each question branches into more questions, and each question leads us deeper into the structure of knowledge. Well, this is why the attitude of the scientist is not to declare certainty, but to cultivate clarity. Not to defend old ideas, but to test them against new evidence. Not to fear anomalies, but to follow them gently until they reveal their meaning. And that approach, patient and curious, is exactly what 3i Atlas deserves. You know, sometimes in science, the hardest thing is to resist the urge to frame every puzzle as a crisis. Humans are storytellers, after all, and puzzles tempt us toward dramatic narratives. But most of the time, nature is not hiding a secret. It is revealing a complexity. And that complexity deepens our understanding, not overturns it. 3. Atlas may be one such example. A comet that simply reminds us that the diversity of icy bodies in the galaxy is far wider than our limited experience. A reminder that our solar system is not the template for all planetary systems, but merely one example among billions. A reminder that physics remains true, but our models of how physics expresses itself in different environments must continue to evolve. Well, this all brings us to a larger philosophical truth, one that echoes across all scientific disciplines. The universe is not simple, but it is intelligible, and the process of understanding it requires humility, persistence, and imagination in equal measure. When we adopt this attitude, anomalies stop feeling like threats and start feeling like invitations. You know, maybe the most beautiful part of this is that science becomes a kind of conversation. The universe presents an observation. We respond with a hypothesis. The universe answers with another observation. And on it goes, a gentle and endless dialogue. 3i Atlas is one voice in that cosmic chorus, a small icy traveler offering a quiet sentence in the long story of the cosmos. And, if we listen carefully, the sentence it offers might be something like this: do not rush, do not assume, let the data mature, let the models breathe, let wonder lead the way. Well, with that spirit in mind, the path ahead becomes clearer. If 3i Atlas is as unusual as it seems, then we must gather more observations. We must refine the models of its jets, its energy balance, its interior. We must compare it not just to solar system comets, but to the growing family of interstellar visitors. We must widen our search for patterns and be open to the possibility that new classes of objects are drifting through our neighborhood. You know, this leads us toward the next question, one that feels both scientific and deeply human. If caution guides our interpretation and curiosity fuels our exploration, then what remains to be discovered about 3i Atlas itself? What lingering mysteries does it carry? What unsolved questions rise like faint signals from its structure? And that, well, leads us gently toward the next chapter, where we turn from caution toward possibility, from patience toward speculation, and from humility toward the open horizon of the unanswered questions that 3i Atlas still holds in the quiet of its drifting form. Well, you see, as we follow the thread of scientific humility into the quiet space that lies ahead, something begins to shimmer at the edge of our curiosity. Because after caution comes possibility. After restraint comes imagination. And somewhere between those two, in the soft middle ground where questions breathe, lies the field of the unsolved. The open questions, the lingering mysteries that hang around 3I Atlas like a faint halo, subtle and persistent. And, perhaps this is where the story becomes its most human, because asking what we do not yet know is, in a way, our most universal instinct. You know, when we look at 3I Atlas through the lens of everything we have explored so far, we see a mosaic of puzzles, each piece unusual, each detail a little off-center, and none of them, not one, sits so far outside the boundary of physics that we must rewrite the laws of nature. But together they form a pattern that whispers gently that we are missing something. A pattern that feels like a constellation seen from a strange angle. Familiar points, but arranged in a way we have not yet imagined. Well, perhaps the most obvious unsolved question is the one that threads through every chapter so far. The energy dilemma. How can a nucleus only 5.6 kilometers across sustain jets that stretch millions of kilometers into space? How can it maintain sublimation rates that demand an effective absorbing area far larger than its physical size? And why does it achieve this without fragmenting? These questions remain open. They sit like small lanterns along the path, illuminating the incompleteness of our models, not breaking them, but inviting refinement. And, perhaps the answer lies in a surface far more complex than we assume, or in chemistry, not represented in our local comets, or in an internal structure shaped by pressures and temperatures we have never observed, or perhaps in some subtle thermal process that allows heat to penetrate the interior more efficiently. Each of these possibilities remains on the table, but none of them closes the question. That is the beauty of it. The question remains alive. You know, another unanswered mystery is the distribution of volatiles inside the comet. If 3I Atlas contains deeply buried pockets of exotic or highly volatile ices, those pockets might feed long-lasting jets. But how many pockets are there? How deep do they go? Are they remnants of the comet's formation, or were they carved later by collisions or thermal events? The internal architecture of 3I Atlas is invisible to us. We infer it only from the jets, from the brightness gradients, from the smoothness of the halo, from the stability of the nucleus. But inference is not certainty, and this uncertainty is one of the most tantalizing aspects of the comet. Well, you see, the lack of fragmentation also raises questions about the material strength of the nucleus. If the comet is dense or strongly bonded, that strength must come from somewhere. Was it forged in a denser protoplanetary disk, hardened by intense radiation, compressed by collisions, reinforced by chemical processes unique to its home system? Or is it simply a statistical outlier, one rare example of a robust icy body? We do not know yet. And in that not knowing, there is room for discovery. And, the jets themselves pose puzzles. Their extraordinary length, their coherence, their stability over time. These traits hint at deep, consistent reservoirs of gas, but they also tell us something about the comet's rotation, about the geometry of the vents, about the interplay between solar radiation and internal pressure. And while we can sketch plausible models, the truth remains elusive. Because we lack the resolution to watch the nucleus rotate, we cannot see the vents. We cannot track the internal heat flow. We can only observe the outgoing streams of dust and gas and trace them back like detectives working backward from footprints in the snow. You know, one of the most striking unsolved questions involves the antitail. Why was it so well defined? Why did it persist with such clarity after perihelion? Antitails are known phenomena, yes, but 3I Atlas displayed one with remarkable symmetry, like a razor-thin sheet of dust perfectly aligned with the orbital plane. It suggests a very specific size distribution of dust grains, a particular geometry of emission, a rhythm in the timing of dust release. These details hint at something orderly beneath the surface chaos, a clockwork hidden in the ice. But again, the specifics remain out of reach. Well, There is also the mystery of the comet's journey before it reached us. How long did it drift between the stars? What events shaped it? What temperatures did it endure? What gravitational tides stretched or compressed it? What collisions carved its surface? Each interstellar object carries a history too ancient for us to reconstruct. And yet, each one also carries trace evidence. The chemical composition, the structure of the nucleus, the pattern of volatiles, the behavior under heat. Together, these traits form a quiet autobiography. We can read the edges of the story, but not the whole of it. And, another unanswered question concerns the future of 3I Atlas. As it drifts back into the deep outer regions of the solar system and eventually returns to interstellar space, how will its structure evolve? Will the volatile pockets continue to sublimate? Will the jets weaken and fail? Will fractures emerge? Will the surface darken further? Will it return to silence? Or will it retain some memory of its passage through sunlight, carrying faint scars of its bright moment near our Sunday? We will not see it again. Its orbit is open. Its trajectory leads outward, never to return. So, this is a mystery that may remain forever out of reach. You know, one of the more subtle open questions is philosophical rather than physical. What does it mean for our models that objects like 3I Atlas exist? How should we adjust our expectations for future interstellar visitors? Should we assume more robust bodies, more exotic chemistry, more complex sublimation patterns? Or should we treat 3I Atlas as an outlier, a single dramatic example in a spectrum of quieter, simpler interstellar objects? We do not yet know which interpretation is closer to the truth. Well, you see, beyond each physical question lies a deeper reflection, a reminder that the universe is not obligated to stay within the narrow corridors of our experience, that anomalies are not threats, but invitations, that uncertainty is not a deferred void, but a canvas. 3I Atlas reminds us that the frontiers of astronomy are not found in tidy equations, but in the spaces where the equations fall short, where the data stretches the model, where the story refuses to end neatly. And, perhaps the most beautiful unsolved question is not about jets or volatiles or structure. It is about meaning. What does it mean for us, here on a small planet in the 21st century, to watch an object from another star system pass through our sky? An ancient visitor carrying frozen memories of a dawn older than our world, a wanderer that traveled longer than the history of human civilization. What does it mean that we, small as we are, can detect such a visitor, can model its jets, can estimate its mass loss, can write stories about it, can wonder about its origin? In that sense, the unsolved questions of 3I Atlas are not barriers, but bridges. They connect us to something larger, something humbling, something beautiful. You know, it is almost poetic how each unanswered question gently nudges us toward new methods, better telescopes, more sensitive instruments, new surveys scanning the sky for faint wanderers, new models that embrace a wider diversity of cometary behavior. 3I Atlas not only expands our knowledge, it expands our ambition. It encourages us to look harder, to ask better questions, to prepare for future interstellar visitors with curiosity rather than certainty. Well, as we let these open questions settle around us like dust in a sunbeam, another thought begins to form in the quiet. If interstellar objects like 3I Atlas carry ancient information, then perhaps one day, with the right tools, we could capture one, study it up close, examine its chemistry not through remote sensing, but directly, touch the material shaped under another star. And that possibility is no longer pure science fiction. Missions have been proposed, trajectories calculated, technologies imagined, and that idea, soft but compelling, leads us toward the next natural question. If 3I Atlas is a messenger from another world, then what would it mean to meet one of its kin directly? To chase an interstellar traveler, to sample it, to bring fragments back to Earth. What would it mean to hold in our hands material older than our planet, shaped in an environment we have never seen? And that, well, is where the story turns next, toward the future, toward what we might learn, and what we might dare to do, as the next wanderer approaches from the dark between suns.